Okay, so we're going to consider the system u double dot plus omega 0 squared equals u minus 2 epsilon c u dot minus epsilon alpha u cubed plus, and this time we're going to have big K times the cosine of omega t. And so in this case, this excitation is strong, K is of order 1. And then the other thing we're assuming here is that this big omega, the forcing frequency, is far away from the fundamental frequency omega 0. Okay, so from here we're going to do our standard expansion for u in terms of ever increasing orders of epsilon. And then we're going to apply the method of multiple scales, and then from there what we'll end up with at order 1 is d0 squared u0 plus omega 0 squared u0, and then this is equal now to k times the cosine of capital omega t. And you should note that the harmonic excitation now appears at order 1, whereas before when we studied primary resonance it was at order epsilon. Okay, so we can solve this order 1 equation, and we'll find that u0 is equal to a of t1 times e to the j omega t0 plus lambda times e to the j capital omega t0 plus complex conjugate terms. And so this first term right here, this is our homogeneous term. And then the second term is our particular integral, or the particular solution. And here lambda is equal to 1/2 times k times the quantity 1 divided by omega 0 squared minus capital omega squared. Okay, so we're going to substitute in our so I seem to have left out the order epsilon equation. I'll add a note somewhere where that is, but at this point it should be pretty standard and easy. You should be able to compute that yourselves. Anyway, we're going to plug it into that. We're going to plug in the u0 solution into the order epsilon equation, and this will result in the following: minus the quantity 2 j omega 0 times a prime plus ca plus 6 alpha a times lambda squared plus 3 alpha a squared times a bar, all of that times e to the j omega 0 t0 minus alpha times the quantity a cubed times e to the 3j omega 0 t0 plus lambda cubed times e to the 3j capital omega t0 plus 3a squared times lambda times e to the j times the quantity 2 omega 0 plus capital omega times t0 plus 3a bar 3a bar squared times lambda times e to the j times the quantity capital omega minus 2 omega 0 plus 3a times lambda squared times e to the j omega 0 plus 2 capital omega times T0 plus 3a times lambda squared e raised to the j times the quantity omega 0 minus 2 capital omega T0. And now we can close our curly brace. Minus lambda times the quantity 2j c omega, capital omega that is, plus 3 alpha lambda squared plus 6 alpha a bar, close the square bracket, multiplied by j omega, capital omega T0, and then plus complex conjugate terms.
On that third line, on the exponential, why we're not multiplying times T naught?
We should be. So right here. Yeah. Good catch. Okay, so this first term in the square brackets here, this term is what we could call our obvious secular term. It's a secular term, well, it's of the form of a secular term of what we've seen previously. We also have two potentially secular terms. The first potential one is what I'm circling in blue right now. And the second potentially secular term is the one I'm circling in purple. Okay, so in addition to those obvious secular terms, we will get a secular term whenever the following equation is satisfied. So depending on what omega is, the two terms here, they may be secular. Depends on the value of capital omega. And that's what we're going to study.
Oh, okay. So, like, 1/3 makes it secular.
Yeah, so the key thing is that they're related by some ratio that's either 3-to-1 or 1-to-3. We'll go take a look at that now. Okay, so we have to distinguish between 4 different cases in our analysis, although really it's only three cases. So first, we can have here just omega being away from 0, omega 0/3, and 3 omega 0. So this is not a resonance term. This is just responses away from resonance. The second case we need to consider is when capital omega is approximately equal to omega 0/3. In this case, this is our super harmonic resonance. And the third case is when capital omega is approximately equal to 3 omega. And you might want to try looking at that fourth case, but that's not possible due to our initial assumptions about capital omega being far away from omega 0. All right, and you should note that we're going to get 3-to-1 resonances here, or 1-to-3 resonances here, because we have a cubic term. If you include other terms, you get other integer ratios, and that's what I'm saying up there in that little green note. And so if you go up to order n, then you can get, let's say you go up to 7, you could get a 7-to-1 internal resonance superharmonic or subharmonic. There's no internal resonance yet, but one of those super or subharmonics. We're only going to consider a cubic case in class at least. In the homework, you might study another case. All right, so let's start off by looking at the non-resonant case, which is the very first one where capital omega is away from 0, omega 0, and 3 omega 0. Oh, and one more thing I should say, when capital omega is equal to 0, that is a special case that we won't cover in this class, but it is in the NAFE book if you want to read through that. Actually, I think it's a problem in that book, but we won't consider it. Okay, so in the non-resonant case, we are going to eliminate the following secular terms. We'll have that 2j omega 0 times a prime plus ca plus 6 alpha lambda squared a plus 3 alpha a squared a bar. This equation must be equal to 0. From there, we're going to expand capital A into a polar form with a real positive amplitude and a real phase. And in that case, we're going to end up obtaining the following. First, we'll obtain that A prime is equal to minus CA. And so we substituted in and then separated real and imaginary parts, and now we're looking at the resulting equations of that. And for the real part, we'll get A prime is equal to minus CA, and that allows us to solve for A, and A is going to be equal to A0 times e to the minus c t1. And then for the second equation, we have omega 0 times A times B prime is equal to 3 alpha times the quantity lambda squared plus a squared over 8. All that times a. And in that case, we can then eliminate an a from both sides of the equation. And we'll get that B prime is equal to 3 alpha over omega 0 times lambda squared plus a squared over 8. And actually, let's substitute in what we found for a above. We'll end up with 1 over 8 times a0 squared times e to the minus 2c t1. And we can close the parentheses there. From here, we can then solve for b, and b will be some b0 plus 3 alpha over omega 0 times lambda squared t1 plus 3 alpha divided by 16c omega 0 times a0 squared times e to the minus 2 ct1. And with A and B now found, we can go back and substitute these in for capital A, which we can then substitute into our equation for U0, and then solve for U of t, which becomes A0 times e to the...
Supposed to be negative 3 alpha over 16. Exponent is minus 2c.
Yeah. Yeah, it should be a negative, you're right. And it shows up as a negative in the next line. So you're right. Let me correct that. All right. So we'll have A0 times e to the minus epsilon ct times cosine. We've got a large expression that's like cosine, so it starts off with omega 0 t plus 3 alpha times lambda squared divided by omega 0 times epsilon t minus 3 alpha over 16c omega 0 times a 0 squared e to the minus 2ct1. In fact, should be 2 epsilon ct plus b0 plus, let me move that over, plus b0 plus order epsilon squared terms plus k over omega 0 squared minus capital omega squared times the cosine of capital omega t plus order epsilon terms. Okay, so this exponential that we have inside the first cosine, we can expand this as follows, as shown above there. And when we expand that, what we end up with is the following. We will end up with u of t is equal to a0 times e to the minus epsilon ct times the cosine of the quantity omega 0 plus 3 epsilon alpha times lambda squared divided by omega 0 minus 6 epsilon alpha c a0 squared divided by 24 c times omega 0, all of that multiplied by t minus 3 alpha times a0 squared divided by 4c omega 0 plus b0 plus order epsilon squared terms. That's everything inside our first cosine, plus then k divided by omega 0 squared minus omega, capital omega squared times the cosine of capital omega t. Then plus order epsilon terms. All right. Okay, so everything encompassed by that green term represents the transient or decaying term with a frequency close to the linear natural frequency or the linearized natural frequency. And then what's highlighted in blue is the steady state term with frequency equal to that excitation. So some things to note first, that free oscillation term, it is decaying, but while it's decaying, its frequency is a function of the amplitude. It's not equal to the linear frequency or the linearized frequency. It is a function of the amplitude. And then as t goes to infinity, that transient term is going to die out, and we're going to be left with only the steady state term that at that excitation of omega, of capital omega. And we should also note that its amplitude is small, and that's because the term in the denominator here is not going to be small. And that's an assumption that we made at the beginning of this analysis. Okay. Any questions so far? All right. In that case, we're going to move on to look at superharmonic resonance. In this case, we're going to use a detuning parameter, and we're going to say that 3 times capital omega is going to be equal to omega 0 plus epsilon sigma. And this is the case where capital omega is approximately equal to omega 0 over 3. so we are forcing at a frequency that is at least 3 times below the linearized natural frequency. But what we're going to find is that there are terms that are, or there's a component excited at that linear natural frequency, despite the fact that we are exciting away from it. And it will not decay. It will remain in the response. That's what we're going to find. Okay, so if we plug this in into, eventually we'll plug this into equation 23, and by doing so, the term that I circled in blue, which I'll scroll up for a moment, this term circled in blue here, that one now will become a secular term, and I'm going to show that in a moment. All right, so that term is minus alpha times lambda cubed times e plus or minus 3j capital omega t0. So we plus or minus because I'm including the complex conjugate, which was stored in that CC term. This is then equal to minus alpha times lambda cubed times e to the plus or minus j epsilon sigma t0 times e to the plus or minus j omega 0 t0, which we can then rewrite as minus alpha lambda cubed e to the plus or minus j sigma t1 times e to the plus or minus j omega 0 t0. Okay. So because of this assumption in terms of what the frequency, that forcing frequency is, we can see that this term has now become a secular term. Secular because we now have this e to the j omega t0 term. Okay, so in this case, in order to eliminate secular terms, we require that 2j omega 0 times the quantity a prime plus ca plus 6 alpha times lambda, 6 alpha times lambda, this is lambda squared times a plus 3 alpha a squared, a over bar, plus alpha lambda cubed times e to the j sigma t1. All of that must be equal to 0. Okay, and just in case you're wondering, the reason that this is a plus right here is that there was a minus sign in front of all of this stuff. So that was then absorbed. That minus sign was then absorbed. Okay, so from here, we are going to expand capital A into a polar representation like normal. We'll then substitute that in, then separate real and imaginary parts, and we'll end up with a prime is equal to minus ca minus alpha times lambda cubed divided by omega 0 times the sine of sigma t1 minus b. And in the second equation, we'll end up with a times b prime is now equal to the quantity sigma minus 3 alpha lambda squared divided by omega 0. That quantity multiplied by a minus 3 alpha over 8 omega 0 times a cubed minus minus alpha lambda cubed over omega 0 times the cosine. Oh wait, hold on. I've been reading from the wrong line. Let's start this over. And this is why you should use pencils. Okay, so we have AB prime is equal to 3 alpha over omega 0 times the quantity lambda squared plus a squared over 8 times a plus alpha lambda cubed over omega 0 times the cosine of sigma T1 minus b, and that is the second equation. So from here, we're going to want to convert this into an autonomous form, just like we've done previously. And to do that, we're going to say that gamma is equal to sigma T1 minus b, and then gamma prime will be equal to sigma minus b prime. And then this then results in the following two equations. A prime is equal to minus CA minus alpha lambda cubed divided by omega 0 times the sine of gamma. And then down here we'll have quantity sigma minus 3 alpha lambda squared over omega 0 times A minus 3 alpha over 8 omega 0 times A cubed minus alpha lambda cubed divided by omega 0 times the cosine of gamma. Okay, we're then going to look for steady state solutions, and we're going to impose what are known as the stationarity conditions, that A prime and gamma prime are equal to 0. And this then allows us to find that minus CA is equal to alpha times lambda cubed divided by omega 0 times the sine of gamma. And then in the second case, we'll get minus, or sigma minus 3 alpha lambda, lambda squared over omega 0 times A minus 3 alpha over 8 omega 0 A cubed. This is then equal to alpha lambda cubed over omega 0 times the cosine of gamma. We're going to square both sides and then add them together to eliminate the trig functions with respect to gamma. And this will then lead to the following, which is c squared plus the quantity sigma minus 3 alpha lambda squared over omega 0 minus 3 alpha over omega 0 times a squared, that quantity squared, and everything in the square brackets multiplied by a squared is then equal to alpha squared times lambda to the 6 over omega 0 squared. From here, we're going to solve for sigma, which ends up being that sigma is equal to 3 times the quantity alpha lambda squared over omega 0 plus 3 alpha over 8 omega 0 times a squared plus or minus the quantity alpha squared times lambda to the 6th over omega 0 squared divided by a squared minus c squared, all of that to the 1/2 power, and that is our equation for sigma. And so once you know sigma, we can then solve for the phase just like we did previously before, using equation 34a. Okay. All right, so the analysis we've done is very much the same as what we did previously in the class. The only major difference now is that we have additional secular terms that have popped up that we've now had to account for, and that it's changed the slow flow behavior. All right, so on the next page, I have gone ahead and plotted the frequency amplitude relationship. In this case, in the first plot I'm showing right now, we are varying the value of lambda, which is then related to the applied forcing level. And in this case, there is no backbone branch that the solutions follow. In fact, as the forcing level increases, what you could consider a linearized frequency, if you were to imagine a backbone for each of these curves, those backbones would actually move and change in frequency as the applied excitation is increased. Here is what happens if you increase the value of that nonlinearity. Yeah, so on the legend it says C, that should be alpha. Those are values of alpha. Yeah, in that code, instead of C here, this should be / alpha instead. So as you increase the nonlinearity and you keep the amplitude the same, again, these curves shift on over. All right, last plot I have here is for if you vary the damping in this case, and in this case, if you vary the damping, then you will just reduce the amplitude of the response as shown here. Okay, so from there, final solution is computed as the following. We'll have A times the cosine of omega 0 t plus B plus K over omega 0 squared minus capital omega squared times the cosine of capital omega t plus order epsilon. So we're going to expand the B there because we just said it was sigma T1 minus gamma. And then we can substitute that in, and what we'll get is that U of t is equal to the cosine of the quantity omega 0 plus epsilon sigma t minus gamma plus, again, k divided by omega 0 squared minus capital omega squared times the cosine of capital omega t plus order epsilon terms. But we already said that omega plus epsilon sigma is equivalent to 3, capital omega, and therefore the final response ends up being A times the cosine of 3 times capital omega t minus gamma plus k over omega 0 squared minus capital omega squared times the cosine of omega t plus order epsilon. So unlike the non-resonant case where we had some decaying exponential term in front of the free oscillation, or this term right here, there's no exponential decay here, meaning that this term does not decay, but it does represent the free oscillation of the system, oscillating at that linearized natural frequency. But it will not decay despite the fact that we have damping, which is a contrary to like the linear system where this transient response or free oscillation would decay. What else? And another thing to note is that the nonlinearity adjusts the frequency of the free oscillation term so that it's exactly 3 times the frequency of the excitation. And then this then makes the response periodic. And you can see that on the next page here where we have some examples. These pictures come from Nafee's book. So on the top left is the free oscillation solution at a period of t, I should say t. And next to it we have the particular response, which is at the forcing frequency, and then what you would actually measure and see, or if you were to simulate it, what you would actually see in the displacement is shown in the bottom middle, which is a combination of these two terms. So despite it being a single degree of freedom system and you're forcing it at only one frequency, we get back a multi-frequency response, and that is purely due to the nonlinearity that exists in this system.
Is it the same as what we say sub-silent system? Because the free oscillation doesn't decay.
Maybe, I'm not familiar, to be honest. Probably not. But in this case, this is a superharmonic resonance, is what it's called. But you should look that up, and next Thursday tell the class. And I'll make a note that you will let us know. In fact, you know what? I'll make that a daily prep assignment for everyone. You asked if it was a self-excited oscillation. Right?
Yeah.
All right. Let's find out. Well, you'll find out, and then you'll teach me as a class. Any other questions? Now you're scared. I mean, that's like a simple Google search and see what you find. I mean, would you rather have a problem for a daily prep? I mean, you should not be afraid to ask questions, and then, I mean, I don't know everything, so I might ask you to find out for me. Okay, in that case, we're going to move on to subharmonic resonance, and we're going to, in this case, assume that capital omega is equal to 3 omega 0 plus epsilon sigma. So in this case, we are exciting above the linearized natural frequency, but we will end up with responses, potentially responses, at that linearized natural frequency. Hence why it's called subharmonic, because it's below the forcing frequency. Okay, so in addition to the usual secular terms, we are also going to have the term that I've listed there. If we go ahead and substitute in the relationship for capital omega, we'll get e to the plus or minus j times 3 omega 0 minus 2 omega 0 plus epsilon sigma, all of that multiplied by t0, which is then equal to e to the plus or minus j sigma t1 times e to the plus or minus j omega 0 t0. So again, we're generating another secular term. And I left the stuff that multiplies this term out when we wrote this expression out. All right, so in this case, in order to eliminate secular terms, we require that 2j omega 0 times a prime plus ca plus 6 alpha lambda squared a plus 3 alpha a squared a over bar plus 3 alpha lambda times a bar squared times e to the j sigma t1, all of that must be equal to 0. Okay, so from there, we're going to again expand A into polar representation. We're then going to find gamma as being sigma t1 and minus 3b in this case. And then this will allow us to produce the following set of autonomous equations. We'll get A prime is equal to minus CA minus 3 alpha lambda divided by 4 omega 0 a squared times the sine of gamma, and then a gamma prime is equal to the quantity sigma minus 9 alpha times lambda over omega 0 times a minus 9 alpha over 8 omega 0 a cubed minus 9 alpha lambda over 4 omega 0 a squared cosine gamma. Okay, so we're going to then study steady state like we always do, and we'll find that A times the quantity minus C minus 3 alpha times lambda over 4 omega 0 times A times the sine of gamma is equal to 0. And then the quantity A times square bracket sigma minus 9 alpha lambda divided by omega 0 minus 9 alpha over 8 omega 0 times a squared minus 9 alpha times lambda over 4 omega 0 times the cosine of gamma, and all of that must be equal to 0. And so one thing that we find immediately is that the trivial solution...
Missing an A on the last time. Or you have to be most only
I keep up there now.
What it is? Oh yeah.
Hold on. There should be an A here. Right here. Yeah, because there was a squared above. So the trivial solution is a possible solution, and this is not just like a boring solution. This is actually a real solution in this case. I know a lot of times we say trivial, we think, oh, that's boring, we don't really care about trivial solutions. But in this case, this is actually an important solution, and we'll see why in 2 pages. Okay, so what we want to study now is what are the conditions for non-trivial solutions to occur. For non-trivial solutions, we end up with 2 equations. First, minus c is equal to 3 alpha times lambda over 4 omega 0 times a times the sine of gamma. And then the second equation is sigma minus 9 alpha lambda over omega 0 minus 9 alpha over 8 omega 0 times a squared minus, well, in this case now it's equal to 9 alpha lambda over 4 omega 0 times a cosine gamma. And we just taken what was in the square bracket and the parentheses down, and then moved the trig functions onto the right-hand side. So from here, we're going to multiply equation 43a by 3. We're going to then square both equations, and we'll add them together. And then this results in the following, that 9c squared plus the quantity sigma minus 9 alpha lambda over omega 0 minus 9 alpha over 8 omega 0 squared is equal to 81 alpha squared lambda squared over 16 omega 0 squared times a squared. Okay, from there we're going to solve for a squared, which results in the following, that a squared is equal to p plus or minus the quantity p squared minus q to the 1/2 power, and then I'll write down what p is. P is 8 omega 0 sigma over 9 alpha minus 6 lambda squared, and then q is going to be 64 times omega 0 squared over 81 alpha squared times the quantity 9c squared plus the quantity sigma minus 9 alpha times lambda divided by omega 0. That quantity squared, and that is q. Okay, so for non-trivial solutions exist, we must have that p is greater than 0, and we also have to have that p squared is greater than q, or equal to q. And so what this then results in is that if you're given a value of lambda, we can find that sigma must be less than or equal to 2c squared times omega 0 divided by lambda squared plus 63 alpha times lambda squared over 8 omega 0. Or if you're given sigma, which you can then find is that the quantity sigma over c minus the quantity sigma squared over c squared minus 63 to the 1/2. This must be less than or equal to the quantity 63 alpha times lambda over 4 omega 0 c, and that must then be less than or equal to sigma over c plus the quantity sigma squared over c squared minus 63 all that raised to the 1/2 power. And if you take that second equation and you plug it into MATLAB and you look for real solutions, you'll get back this curve in black. And then inside this curve is where these subharmonic solutions where non-trivial subharmonic solutions will exist. I mean, for all frequencies, we will have this trivial solution, but it's only within this shaded domain that we'll have these subharmonic solutions. All right, so I need to make a correction to the notes here. So under these conditions, the system will respond in a way that the free oscillation term does not decay. Let me put that in a different color. So it says does, but it does not decay. All right, so it does not decay to 0 in spite of the fact that we have damping. And this is again in contrast to the linear case where that free oscillation response will decay out. And again, same, just like the superharmonic, in this case, the nonlinearity adjusts the frequency of the free oscillation terms so that it becomes 1/3 the frequency of the excitation. And again, the response is periodic. And in this case, the subharmonic solution is approximated as A times the cosine of the quantity 1/3 times capital omega T minus gamma plus K over omega 0 squared minus capital omega squared times the cosine of capital omega T plus order epsilon terms. And so another thing you should note is that although the frequency of excitation is 3 times the natural frequency or the linearized natural frequency, the response is still large in this case, in contrast to the linear case or the non-resonant case. Again, because this is a type of resonance. Okay, so let's take a look at the possible types of solutions that can exist. So this is the plot of the response amplitude, which is A over here. That amplitude versus that detuning parameter sigma, or related to the frequency. And so from over here back, in that case, in this region right here, frequency is over there. The only solution that exists is the trivial response. So in that case, there is no subharmonic resonance term. It's just a 0 response. And then once you cross this threshold where I have a jump here, you suddenly have a trivial stable solution and a trivial stable non-trivial solution. And what can happen, okay, so if this is something we're going to do in a homework because I'm not sure. NAFI says that there's no jumps in this system, on these types of resonances, meaning that if you start on the trivial solution, you will not jump up to the non-trivial. My advisor says the opposite. And so in a homework, we're going to study whether you can make jumps from non-trivial to trivial. And it has a really important bearing on what happens in physical reality. Because your system, if you imagine that it can jump due to small perturbations, if we're operating on this trivial solution and then we hit some perturbation, then suddenly the response can go from 0 to very large, a very high amplitude.
Does that mean, like these stable solutions, one of them has strong stability, not the other?
I don't know. That's one of the things. Well, we're not going to go that far. We're just going to do some numerical experiments. But yeah, I mean, that's something that we could study. You're absolutely right. if this was a full 16 weeks of like,
Yeah.
that's when we would do that.
I'm not just about the velocity, like, just like, for a reason why, like, both of them, like, both of them are stable. And, with a small perturbation from one of them, like, makes sense
Yeah.
that just goes back to the stable solution, to the closest stable solution.
Sure.
Unless the other one has more stability or that can.
Right. And I mean, yeah, you can, again, do a perturbation analysis and study that. In that case, you end up with parametrically excited equations, and you've got to do flow K theory, which, again, we won't cover, unfortunately. It's a very beautiful theory. We just don't have the time. However, I will say that these subharmonic oscillations can have catastrophic effects, and in a book written by this Lefschetz person, he described an aircraft that had the propellers induced a 1/2 subharmonic vibration in the wings, which then induced a subharmonic of order 1/4 in the rudder, and these vibrations are so violent that the plane broke up, actually. So these are real things, and at the bottom of the page, there is the reference for this. Okay. Are there any questions about what we've covered today so far? Mohammed's afraid now.
You can ask me another question, we can take it over.
Okay. So in that case, we're going to start the method of complexification averaging, and we'll see if we finish this or not. If not, then I'll be recording this as a lecture for next week for you guys when I'm gone. All right, so this is a method for studying steady state and transient dynamics of both weakly nonlinear, but more importantly, strongly nonlinear dynamical systems. And it was developed by Leonid Manovich in 1990, 2000, early 2000s. And his implementation is a little bit different than what we do. He does eventually introduce small parameters and then does an expansion based on that. We are going to not do that at all. We're going to study something without any weak nonlinearity in it. All right, before we get to that, first, this method relies on three things. First, it relies on the complexification of the analysis. Second, it relies on a slow, fast partition of the dynamics. And then third, it relies on averaging, which we have not covered, but we will still employ it here. So it relies on averaging. So like I said, it does not employ a formal small parameter like the method of multiple scales or Lindstedt Poincaré or those two methods actually. And instead it relies on an assumption about the dynamics itself. And that assumption is specifically that there is a single fast frequency in the response, which we'll get to in a moment. All right, so the main idea is that you can make this slow, fast partition in the dynamics and then consider separately the slow dynamics. That's that slow modulation. You can see I've, again, put in our fast oscillation with a slowly modulating amplitude. So the idea is that we can separate and consider each of them separately, the slow and the fast dynamics. And so we end up defining just as a brief preview, we end up defining a complex variable psi of t as being equal to x dot of t plus j omega x of t. From there, we let psi of t be approximately equal to a phi of t times e to the j omega t. And here, this phi, this is the slow part, and the e to the j omega t, this is the fast part. All right, so the core assumption we made here is that there's only one fast frequency, omega. And at the end of these notes, I have a numerical example where this method fails because there are actually two, or multiple at least, I think there are two, but there may be more. There are multiple fast frequencies in the response. But anyway, our core assumption is that there's only one fast frequency. All right, this then allows us to find an autonomous system for phi in the form phi dot is equal to some function of phi, f of phi. And then before we get the slow flow dynamics that governs the evolution of that slow amplitude. Okay.
So the first question is psi of t or psi dot?
The first portion was psi of t. All right, we're going to go through this method using an example problem. And we'll see how it's applied there. So in our case, our example will be x double dot plus c times x dot plus alpha x cubed is equal to k times the sine of omega t. And one thing you should note here is that alpha times x cubed, this is a strong nonlinearity. And another thing you should note is that there's no linear term. There's no omega 0 squared times x. So there's no linear generating term, and that means that you cannot use the method of multiple scales, you cannot use Lindstedt Poincaré, and you cannot use the averaging method either, because there's no linear generating term. So CXA is the only analytical method that I know of that can be applied to equations like this. So if you encounter a system that does not have a linear term in it, you cannot use multiple scales, you cannot use Lindstedt Poincaré or averaging, period. You have to use CXA, and maybe there are new methods out there as well, but as far as I know, there's only CXA. Okay, so we are going to define a complex variable psi, and it's equal to x dot plus j omega x, and then the complex conjugate then is x dot minus j omega x. From there, we're going to solve for x, x dot, x double dot, and x cubed as well. Well, we're not going to solve it. I'm just going to write it down here. But it is in the appendix at the very last page of your notes. All right, so in this case, x ends up being psi minus psi over bar divided by 2j omega. X dot is equal to psi plus psi over bar over 2. X double dot is equal to psi dot plus psi over bar dot over 2. And this, I've just taken a time derivative of x dot here. In green, you can also use another definition for x double dot. You will see this definition a lot when you read about this method. In fact, I don't think anyone ever uses the one that I've put up here. But in the end, the results are the same. It doesn't matter for one. And I personally prefer this because you end up with a nice symmetry in the complex conjugate terms. Whereas you do not end up with that when you use this version. However, the results are the same. Ultimately, the results end up being exactly the same. So it doesn't matter what you use. So x cubed here is going to be equal to j over 8 omega cubed times the quantity psi minus psi over bar, and that quantity cubed. And those are derived in Appendix B. All right, I wrote vector field here. We should more accurately say, well, the ODE to be more clear of what I mean. So we're taking those definitions and we're substituting them into the equation of motion. That's what we're doing. All right, and this will then become psi dot plus psi over bar over 2 plus c over 2 times psi plus psi bar plus j alpha over 8 omega cubed times psi minus psi over bar, that quantity cubed, equal to k over 2j times e to the j omega t minus k over 2j times e to the minus j omega t and the second term here is this is usually what we would end up putting in the complex conjugate or the CC. In this derivation, we're going to write out for the next 3 steps. We're going to include every term, and then we're going to lump a bunch of stuff into complex conjugate, into CC. Just so you have an opportunity to see what they look like. All right. So from here, we're going to partition this response into slow and fast components. We're going to say that psi of t is equal to some phi of t times e to the j omega t. And again here, phi is our slow part, and e to the j omega t is our fast part. And here we are assuming there's only one fast frequency, omega, and if there are multiple fast frequencies in the response, then this method does break down. And you potentially could assume there are more fast frequencies, but the analysis is already heavy enough that I wouldn't recommend it. And you wouldn't be asked to do that here, at least. All right, so for the complex conjugate, we're going to get psi over bar is equal to phi over bar of t times e to the minus j omega t. So again, these phis here are complex. They are not real numbers. They are complex. Okay, again, this is our big assumption that we can do this partitioning, and there's only one fast frequency, and it's what forms the ansatz, or the educated guess, for this problem. We're going to then substitute this in, and what we will get is that 1/2 times the quantity phi dot e to the j omega t plus j omega phi e to the j omega t plus phi over bar dot e to the minus j omega t minus j omega phi over bar e to the j omega t plus c over 2 times the quantity phi times e to the j omega t plus phi bar e to the minus j omega t, that quantity there, plus j alpha divided by 8 omega cubed times the quantity phi e to the j omega t minus phi over bar e to the j omega t. This quantity cubed is then equal to k over 2j e to the j omega t minus k over 2j e to the minus j omega t. And yep.
So aren't we supposed to have the negative exponent with every phi bar?
Yeah. There's one missing right there,
And what is the top?
right there. Is that it? I think those are the only ones. Yeah. Yeah, you're right. Because it should be a complex conjugate. All right, so let's expand the term here. I'll bleed that up. Let's expand the term phi e to the j omega t minus phi bar e to the minus j omega t cubed. This ends up being phi cubed e to the 3j omega t minus 3 phi squared phi bar e to the j omega t plus 3 phi over bar squared e to the minus j omega t minus phi over bar cubed e to the minus j omega t. Actually, that should be minus 3j omega t. All right, we're going to write one more line and then we'll be done. And then the rest will be recorded for pre-recorded lecture. All right, so from here we're going to, again, I guess, substitute the expression we just derived and then collect all of the terms. And what we'll end up with is the following, that phi dot over 2 plus j omega over 2 times phi plus c over 2 phi minus 3 j alpha over 8 omega cubed times phi squared phi bar minus k over 2j, all of that multiplied by e to the j omega t plus j alpha over 8 omega 3 omega cubed phi cubed e to the 3j omega t plus quantity phi bar dot over 2 minus j omega phi bar plus c over 2 phi bar plus 3j alpha over 8 omega cubed times phi bar squared times phi plus k over 2j, all of that multiplied by e to the minus j omega t minus j alpha over 8 omega cubed times phi bar cubed e to the minus 3j omega t, and all of that is equal to 0. And what I'm going to circle in blue here, is the complex conjugate of what I didn't circle. So when we say plus CC, we're lumping everything in this blue circle in there. So that being said, when you're doing the homework, you might want to just write out all of the terms if you're not used to doing this, being able to recognize what you should pull out of the CC and what you should keep in it. You might want to just keep all the terms, and then once you find something like this and you recognize, oh wait, these two terms are just the complex conjugate of the uncircled ones, then you can lump them into the CC. With that, we are going to be done.